This is Dr. Carroll, and this video is about linear programming, including the Simplex algorithm. So what are we talking about when we're talking about linear programming? What we're trying to do is find a set of coefficients that maximize or potentially minimize a linear function subject to constraints. For example, this could apply to voting constraints. It could apply to flight crews. It could apply to anything that has a number of constraints and we want to efficiently solve for the best answer. So we could, for example, be seeking to maximize 3 times x sub 1 plus 5 times x sub 2, but it's subject to the constraints that the sum of those two variables has to be less than or equal to 4, and that x sub 1 plus 3 times x sub 2 is less than or equal to 6, with the non-negativity constraints that on both x1 and x2. So this could apply to airline crew scheduling, transportation network planning, several other network planning situations, oil exploration and refining. So a company can only afford to put in so many drill sites, so which ones should they choose? And a number of other applications. Let's make sure we've established some terms before we jump into this more. A linear function is one that we have a function of several variables, and that means they have coefficients a sub 1 times x sub 1 plus a sub 2 times x sub 2 is going to be the function that we're working with. That can be succinctly expressed as the summation of the coefficient times the variable for all, going through each of the variables, naming them by, referencing them by j from 1 to n. In terms of linear constraints, we have both linear equality, where we have a function assigned to or set to a value, and linear inequalities, where it's either less than or equal to or greater than or equal to. So graphically, what does this look like? If we have a number of constraints in 2 dimensions, we can picture this. Now for real world problems, the dimensions get much higher and it doesn't work to visualize it. But this can help us build some intuition and some understanding about it. So we're talking about a feasible region. It's a convex region. And what it is it's the intersection of all these constraints. Here in this diagram, it's the blue area. And so we also have an objective function that we have, and we say, okay, in this feasible region, we want to maximize some objective function. And so we're looking for the optimal solution. So while there are many solutions that will work, we want the optimal one. Here, the objective function is x sub 1 plus x sub 2 equals 8. And so, the objective function is x sub 1 plus x sub 2. And so we're trying to maximize that. So when that equals 8, that is the largest, has the largest value that is in the region here. And so that's a 2D demonstration of what we're about and what we're trying to accomplish. Let's talk about the Simplex algorithm. It's been around for many years and it's known to be exponential, but that usually doesn't happen, which is good news. So there's a couple different stages. So the first stage is standard form. And so we want all constraints to be inequalities, and we're trying to maximize an objective function, and it's subject to some constraints, and we have non-negativity constraints. So how do we get to standard form? Well, there are 4 conversions to convert to standard form as outlined in Introduction to Algorithms, 3rd edition. First, we're going to convert minimization objective function to maximum objective function. Then we're going to replace non-negativity constraints. Third, we're going to convert equality constraints to inequality constraints, and lastly, all greater than or equal to inequalities to less than or equal to inequalities. So step one, if we actually have a minimization objective function, that's easy. We can just do the opposite and maximize the negative of that by negating all of the coefficients. Step two, replace non-negativity constraints. This one is a little less straightforward. So if we have our constraints, but not all of the constraints have a non-negativity constraint, then what we do is we artificially introduce one by substituting all occurrences of that variable with two variables and we typically do it with similar names just to keep track of it, but one minus the other. So here, x sub 2 does not have a non-negativity constraint in the original problem, and so we need to introduce one. And so while there was only two variables initially, now we have three, replacing all x sub 2's with x prime sub 2 minus x double prime sub 2. And then we're distributing coefficients accordingly. And then we also introduce that both x prime sub 2 and x double prime sub 2 are subject to non-negativity constraints. Step 3, converting equality constraints to inequality constraints. So if we have an equality constraint, then we need to not change the problem, but we need to reformulate it as two inequalities. So if we have a function that's equal to b, we can say that it is both less than or equal to b and that is greater than or equal to b. Now that feels like a huge inefficiency, but we need, for the algorithm to work, we need to get it within those, we need to set up things properly. So we can do this. So here we have x sub 1 plus x prime sub 2 minus x double prime sub 2 equals 20. We need to replace that with two equations. And so we haven't changed the constraints here. We've only expanded them, but in reality, the only way both of those equations could work is if they're equal to. Now that we've introduced a greater than or equal to constraint, we need to change it to a less than or equal to constraint. So every time we have a function that is greater than or equal to b, we can just multiply both sides of that inequality by -1, applying it to all coefficients and also to the right-hand side. So we can apply that to the constraint we just introduced, x sub 1 plus x prime sub 2 minus x double prime sub 2 greater than or equal to 20. We can negate all of the coefficients and also the right-hand side, so that now we have all of the inequalities are less than or equal to, except for the non-negativity constraints. Okay, there we go. That's how we convert it first. And so now we need to go from standard form to slack form. Slack is we're going to capture the difference between the two sides of the inequality by making them inequality, and to introduce a variable for what that is. So if we have a function that is less than or equal to b sub I, what we could do is subtract that function from both sides. So we have 0 less than or equal to b sub I minus all of the coefficients times the variables, but then capture that slack and assign it to a variable s sub I, and then also have the constraint that s sub I has to be greater than or equal to 0. So then with those two, the equality and the the non-negativity constraint, we haven't changed the original problem. Now for notation, instead of s sub I for a slack variable, we're going to continue with the x variables just to make it easier, and picking up the numbering after the ones that originally showed up in the problem. So here we have all the constraints are equalities except the variables that are required to be non-negative. And so now this is in slack form, and we're ready to apply the simplex algorithm to solve it. So let's introduce some vocab so that we can talk about this very concretely. We say that the basic variables are on the left side of the equalities, and the non-basic variables are on the right side of the equations. But these will change each iteration through the simplex algorithm. So let's do an exercise here. Given, let's say we've already established this maximization problem and these constraints in standard form. Now we want to convert that to slack form. So we're already in standard form. We just need to convert it to slack form. So we need to convert these inequalities to be equalities and introduce slack variables here. In addition, we use z for the optimization function at the top. And so that would look like this: z equals 2 times x sub 1 minus 6x sub 3. And then we have our constraints are now equalities. So x sub 4, x sub 5, and x sub 6 are our basic variables, and then we have our other variables showing up on the right. Now we're ready to apply the simplex algorithm. So this is in slack form, but I want you to notice that there are 3 equations here and 6 unknowns. And so that means we have an infinite number of possibilities. What we're trying to do is maximize them according to the optimization function. What we're going to do is first, we're going to set all the variables on the right hand side to 0. This will make things easy for us. So x sub 1, x sub 2, x sub 3, we're going to set to 0. So that's going to make x sub 4 30, x sub 5 24, x sub 6 36, and z equal to 0. We'll come back to this a couple times. This should never change as we're going through it. There's a lot of simple math going on, so if these values change, meaning that this set of values should always hold true. So our goal is to rewrite these equations though, so that the objective function uses different variables. And by rewriting the equations, it changes the basic solution and therefore the objective function. We're not changing the equations or the system or the problem. What we're doing is increasing the objective function by rewriting the equations. Let's see that. We're going to do this with pivoting. We're going to select one of the non-basic variables, and we'll call it x sub e. E is for entering. And that's going to be the coefficient in the objective function. Oh, sorry, with the constraint that the coefficient in the objective function has to be positive, because we're trying to maximize. Then we're going to increase x sub e as much as we can. And then we're going to switch x sub e with a basic variable, and we'll call that x sub l. L is for leaving. So how do we determine what is our entering variable here? With the objective function 3x sub 1 plus x sub 2 plus 2x sub 3, x sub 1 has the largest positive coefficient, So we're going to choose that. It has the most potential, you could think of it as, to increase z. So we're going to start with there. So x sub e is x sub 1 to begin with. Now, we now want to look at the different equations, our constraints, and see what do they mean in terms of x sub 1. For the first one, the equality set to x sub 4, the largest that x sub 1 can be is 30. Because of all our non-negativity constraints, we can ignore x sub 2, we can ignore the term x sub 3, so that leaves 30 minus x sub 1, but x sub 4 has to be at least 0. So the largest the x sub 1 can be would be 30, making x sub 4 0. And so we know that x sub 1 has to be less than 30 to make all these constraints work. Now x sub 5 has to be less than or equal to 12, but x sub 1 has to be less than 12 due to the constraints in the equation for x sub 5. For the equation with the equality x sub 6, then x sub 1 can be at most 9. What we do is we choose the tightest constraint, so we choose x sub 6 as our leaving variable, and we're going to pivot now. So we're going to solve, we're going to take x sub 6 and solve it for x sub 1, and then we're going to substitute in that equation in all of our other equations. As you can imagine, this gets pretty messy pretty quickly. So we have our new objective function shown here in equation 26, and we've rewritten the equation assigning x sub 4 using equation 25, and also the equation for x sub 5 using equation 25, and then we use equation 25 then as one of our constraints. So now let's take a moment and pause and verify that x sub 0, x sub 1, x sub 2, x sub 3 were all set to 0. Then we should have x sub 4 equals 30, x sub 5 equals 24, and x sub 6 equals 36, and the objective function equals 0. Well, let's see here. The objective function goes pretty quick because we have 0 plus 0 minus 3 times 36 divided by 4. Well, 36 divided by 4 is 9. 3 times 9 is 27. So 27 minus 27 is 0. And we could verify that for all of these to make sure we didn't make any mistakes. This is just to reinforce that we haven't changed the problem. We've only changed our equation. We're trying to maximize z. So now, so what has changed though is that our basic solution, setting all the variables to 0, we get different values for z and the basic, setting all the non-basic variables to 0, then our basic solution has changed. Notably, z is now 27, a lot more than 0. So that was the first iteration. Now let's apply that again. Now we need to determine x sub e. We're looking for the largest positive coefficient in the objective function. And so that would be x sub 3. It has the largest coefficient. So now we need to look and see what for our constraint equations here, which one has the tightest constraint. x sub 3 has to be less than or equal to 18 for the equation setting to x sub 1, whereas it needs to be less than or equal to 42/5 for x sub 4. For x sub 3, it needs to be less than or equal to 3/2, so or the last equation. So we're going to use x sub 5 as our leaving variable because it's the tightest constraint. And so once again, we're going to solve that last equation for x sub 3, which is our entering variable. And then we're going to rewrite all the equations again. Our original set still applies, but what we've done is setting our non-basic variables to 0, we get a new basic solution. Notably that z has gone up from 27 to 27.75. Small gain, but a gain. That's the second iteration. Now, our third iteration, we want to continue to increase our objective function. So we're looking for the largest positive coefficient variable, and that would be x sub 2. Now we look to maximize the objective function using x sub 2, but we need to know what the tightest constraint is. Notice that the last equation, setting equal to x sub 4, it has x sub 2 with a positive coefficient, which means its constraint is it has to be less than or equal to infinity. That's not very constraining, and so we're not going to choose x sub 4 as our leaving variable. We choose x sub 3 as the leaving variable, and if you'll remember from previous iterations, we're going to solve for our entering variable, change that equation to solve it for the entering variable, and then rewrite all the other equations substituting in x sub 2, and then we have our new set of equations. Now we have a new basic solution. Notably, z is equal to 28. It went up again. Well, that concludes this video about linear programming and the simplex algorithm. Thank you for watching.